All right, sorry about that. So my little storage disk was almost full. I'm glad we were able to get through all of that video. So we balanced those equations, and now the next thing we need to look at is what we call evidences of a reaction. Many of you have already learned much of what we were talking about here through other times in our class. We have talked about what evidence do we have that a chemical reaction is taking place. And that evidence are things like the light that's being given off during the burning of a reaction. We also can look at the formation of bubbles and things like that. But there are literally 4 what we call visible evidences. Sometimes when we say that it's visible, it's because we have to do some type of, I don't even know what you want to call it. We have some type of observation or measurement, like you have to use a thermometer or you might have to use something else. But there are 4 visible evidences that we can see using our senses. The first one is the formation of a gas. You did this in the lab on Tuesday of last week, where you added calcium chloride and baking soda and water and mixed it together and it formed a gas. The evidence a reaction took place was those bubbles, the formation of a gas. The second visible evidence is when a solid forms or a precipitate. A long time ago we did a couple of reactions where you mixed these 2 clear solutions together and it got cloudy. Or you mixed a solution and you saw these little solid particles building at the bottom of the container. The formation of a solid is called a precipitation reaction, and that solid forming is based on some rules that we're going to have to learn later on. The third visible evidence is a color change. Now this is also very tricky. Just adding food coloring isn't a color change. That's not what we're talking about. What we mean here is like you take a piece of paper and you burn it and it turns black. Or you take 2 chemicals that are clear solutions, you pour them together and it turns yellow. Things like that. That's the type of color change. A non-expected color change is what we're looking at there. And then the fourth one is when energy is absorbed or energy is released during the reaction. So again, sometimes we don't see these. If I mix 2 chemicals together into a container, you may not see that there's energy being released. It's like, well, they just mixed, so what? If we put a thermometer in, you would see the temperature rising or the temperature getting colder. In class next week, I'm going to show you a few demonstrations of these types of things where it doesn't look like anything's happening, but it gets really cold. Or the other way around. It looks like, okay, what's happening? It just got hot. So what? That energy being absorbed or energy being released is visible evidence of a chemical reaction. All right? These are the visible things that we can see. There are other things that make the reaction actually take place. Those are called driving forces, and again, we'll talk about those in a couple weeks. What is the force that's making these chemicals do whatever it is they're doing? Why do they react? Those are not visible evidences. Those are driving forces, all right? So the last thing we need to talk about are these patterns that we were discussing before. There are some patterns that we can start to look at and see what's taking place to prove a chemical reaction and also to be able to predict that reaction. So for our class, there are going to be 5 primary types of reactions. These 5 reaction types are what you need to be aware of. They are kind of related. The first one is called synthesis, or another thing in other books and other places, they call it a combination reaction. Because what's happening is we're going to combine 2 or more elements in order to form only one product. It's combining. Obviously, that's what has to happen, is a combination. This is the fancy science word for it is synthesis. I am putting things together. I'm synthesizing one new product. It can be 2 or more elements or 2 or more compounds or an element and a compound. Anything that there's multiple reactants to form one product. That is a synthesis. The reverse of that is called decomposition. There is one reactant and we're going to do something to it to cause it break apart into multiple products. So this would be heating up a substance and it decomposes into 2 gases. Or I run electricity through a substance in order to break it apart into 2 different elements. That is a decomposition reaction. Anytime you see only one reactant, you know it has to be some form of a decomposition reaction. The third is called a single replacement reaction. In a single replacement, it's exactly like it sounds. One element is going to react with something else, react with another compound, and one of its particles is going to trade places. I'm going to show you we call it the generic form of that reaction in just a few minutes, but what happens is it looks kind of like this. Let's see if I can get in the light. We have one thing reacting with a 2 thing, and this 1 comes in and bumps it out of the way, and you get a new product of 2, and the 1 gets left over. So it's going to trade places with it. When I show you the generic equation, it should be, I'll explain it again and make a little more sense. The other is called a double replacement reaction. So with this, it's 2 compounds that are usually ionic compounds, and when they get mixed together, they're going to trade their partners. So it's an anion and a cation combined together with an anion and a cation that are combined together, and when they trade partners, they can only line up in a very specific way. Cations cannot react with other cations. Anions cannot react with other anions. They have to stick together with the opposites. Cations and anions can only go with their opposites, all right? So they're going to trade, again, when you see the generic equation, that might help you out a little bit. And the last type of a reaction that we're going to deal with is called combustion. Combustion is burning, or whatever you want to call it. Sometimes I say burninating. So combustion is a fuel of some kind is going to combine with oxygen. Hopefully you recall from previous life experiences. In order to burn something, you have to have oxygen available. If you take a candle and you put a lid on top of it, after a few seconds, the burning goes away. It goes out because there's no oxygen to support the combustion. So the fuel, whatever it is, reacts with oxygen, and the byproduct of this reaction, the products that are being made, are always water, H2O, and carbon dioxide, CO2. That is the only products that we will deal with in our class. Real combustion has other things taking place because, like a piece of wood or a log or something else might have other compounds involved in it. So when it burns, it releases a couple other things. But the primary combustion is this, a fuel with an oxygen to produce water and CO2. All right? So here's what those generic equations look like. For a synthesis or a combination reaction, we take either element A and element B and we stick them together to form this compound. Now remember, addition is commutative. It doesn't matter which order I put A plus B. So even though I wrote this compound AB, theoretically we could have had B plus A forming AB, right? A is always going to be the cation, B will always be the anion, and so you write them in that order. Don't get so caught up in, well, they're not written in the right order. You have to think about what's going on. If it's a metal reacting with a nonmetal, the metal always gets written first in the compound form, okay? Metals always go first as a compound. The decomposition is the exact opposite. We take something, some compound of some kind, and we have to run energy through it of some way, whether that's heat or electricity, or it's not even just banging on it with a hammer. That won't work. That's just breaking that thing apart. In order for a chemical reaction to take place, there has to be something causing those parts to break apart to reform multiple products. One reactant, multiple products. Synthesis or decomposition is multiple reactants to form one product. All right? So that's those first two. Notice that they're the reciprocal of one another. Synthesis reaction's opposite is decomposition. The opposite of a decomposition is synthesis. All right? Single replacement can do one of two ways, and this is where I said you'll have to re-explain it again. In a single replacement reaction, element is going to react with compound. It's always an element with a compound. However, what those elements and compounds are going to control what type of a reaction takes place. For this, A bumps into these things. So this element goes into the system, bumps into this compound, and it says, C, you are in my way. I want to bump you out of the way to form a new compound called Ba, and now C is free to be an element all by itself. This type of a reaction is called anionic replacement, or anionic single replacement. Okay? Because A is going to replace the anion, the negatively charged particle. In this situation, A has to be a nonmetal. Okay? A is a nonmetal, BC is some compound, and the nonmetal bumps into it, pushes the anion out of the way, forms this new compound called Ba, whatever that would be, and then C is left over. Now again, I'm kind of simplifying this. Realize that if the chemical formula needs like subscript numbers, you have to include those as well. So like if you're making, I can't even think of one off the top of my head that works. So if you're making something that the formula has a subscript number, this is just telling you how they go together in which order. You still have to write proper formulas from those things, right? The other type is called cationic, where A is some type of a metal or hydrogen reacting with a compound, but now A bumps into this thing and pushes B out of the way to form this compound called AC, whatever that would be. Again, don't get stuck on it having to be that absolute ratio, because you have to use the numbers of subscripts in order to keep it a proper chemical formula. So A bumps into B. B flies away and becomes an element by itself. We form new compound AC, and this will change the color so you can recognize it. This is called cationic single replacement, because we are replacing the cation. So single replacement can do one of two things. Either it substitutes in for the nonmetal or it substitutes in for the metal. One element reacting with a compound and they trade partners. Okay? Double replacement is similar, where I talked about it a moment ago. We have compound and compound, right? AB is some compound where A is the cation, B is the anion. CD is another compound. C is the cation, D is the anion. And now when these things come together and switch and trade partners, there is no possible way for A and C to go together. Hopefully you remember this, because when we talked about writing formulas from names and coming up with compounds, you cannot put two positive elements together because the total charge won't add up to 0. I can't put B and D together in this reaction because I can't get A and C. So what happens is it's like square dancing and they have to trade partners. A is going to hook up with D, C is going to hook up with B, and we end up with these compounds AD and CB. This is a double replacement reaction. Okay? The last one, combustion, is a little bit different. The fuel is always it's called a hydrocarbon. There's carbons and hydrogens stuck together, and as a result, when we burn it with oxygen, that's when we end up with these products of water and carbon dioxide. These become really, really complex. You can have gasoline that has lots and lots of carbons and lots of hydrogens, and when you burn them, you get lots and lots of water and lots of carbon dioxide. This is part of why people want to eliminate our fuels of burning them, because when you burn a fuel that contains carbons and hydrogens, you're always going to get carbon dioxide. And so people are thinking that as a result of us burning gasoline, burning coal, burning wood, we're producing all this carbon dioxide and it's changing our environment. So the problem is these fuels are really, really cheap. If you could somehow figure out just hydrogen, the only product you would make is water. So if I were burning hydrogen, I would be making water, but it's really, really hard to get hydrogen all by itself. I would have to use energy to break water apart to make the hydrogens to be able to burn it to become oxygen, and it just becomes this vicious cycle, and you keep working on things like that. So again, with the two different videos we just made, I'm kind of at a point where I need to stop again. I need to do another part 3 next week where we start looking at how to predict the products, how to predict what we're going to be able to do, and come up with formulas from names, names from formulas, and predict them. I think this is about where we need to be in terms of what's going on. Again, remember, when we're writing chemical formulas, we usually have gas, liquid, solid, or aqueous to describe what state of matter is working with them. Whether that be gas, or liquid, or solid, or aqueous. If you see this in the chemical formula, you need that to understand what's taking place. When we start to get to predicting products and figuring out driving forces, these will become important again. But what it really does is it just takes up a lot of time writing down the chemical symbols and writing down the states of matter. So we eliminate the states of matter and do just the symbols, because that's all we really need to know. When you start to get better at this, that tends to be what happens. Again, in class, we're going to practice balancing equations. We'll also practice looking a little bit more at these visible evidences, and we'll talk a little bit more about these 5 different categories of reactions. With this, you have a lot of things that you can still work on in Moodle. You can now work on the review assignments if you haven't. We're going to do those in class on Tuesday and Wednesday. You can also work on balancing equations. You can also now work on another one that should show up sometime over the weekend. And as you continue working through these, this is how we're going to start to understand that we know what we're talking about. We'll continue to work on other things in class. Thursday of next week, we will do a lab called types of actually, I don't even know what it's called, but it's about the types of reactions, and we'll be able to recognize a chemical reaction occurring. Hope you had a great weekend. We'll see you in class. Bye-bye.